Okay, friends. So today we will discuss about the FET biasing and some other terms which are used for the field effect transistors like transconductance, resistance RD, and other terms. Okay, so let's start with the today's session. So yeah. So in the previous lecture, we have discussed about the MOSFETs. Okay, so this is lastly we have discussed about the enhancement MOSFET, its characteristics. Okay, P channel enhancement MOSFET and N channel both we have discussed. So these were the symbol lastly we have shown you. Again, then we have conducted a quiz. Now today I will explain you about first CMOS and then we will move further. CMOS, you can say it is complementary MOSFETs. Okay, so P channel and N channel MOSFETs both are combined here to develop the CMOS. Okay, now why it is called complementary MOSFET? Okay, complementary MOSFET, the name itself says that it is complementing each other. Okay, so there are two kinds of things used over here. One is called P channel MOSFET and one is called N channel MOSFET. So whenever P channel MOSFET will be on, N channel will be off, and vice versa. That means whenever P is off, N channel will be on, and whenever P is on, N channel will be off. Okay, so now construction wise, you can see over here. So over here, there is, you can say your, you can say this is your P channel MOSFET and this is your N channel MOSFET. Okay, so now to make this CMOS, we have to first take N type of substrate. Okay, now if you have N type of substrate, you can definitely make P channel MOSFET, because in P channel MOSFET we need to have N type of substrate, and then we were adding, you can say, P type of materials. Okay, and then here it is a channel between this two P type material. Okay, so this is, you can say, your P type of sorry, this is your N type of sorry, it is of P channel MOSFET. Now for N channel MOSFET, we will take P type of substrate and we will be having N material. Okay, and there will be N channel in between them. Now you will be wondering, what is this? Okay, so if you are making CMOS, then this is added on this side, this is added on this side. So whenever you are making P channel MOSFET, on that side we have to add this one N material, on N channel MOSFET we have to add one P material. Okay, so now if you remember that there will be in MOSFET we will be having one terminal that is drain, one terminal that is source, one that will be having, you will be having source. Okay, so source, and then you will be having substrate. Okay, so now this is intermediate, you can say, terminal, that is gate. So in between there will be MOSFET. This is directly connected with them. So uh, then over here, let us see for this also. This is source, this is drain, directly connected with the P. This is gate, there will be SiO2 layer in between. Okay, now what you have to do to make CMOS, you have to combine the gate of this P channel MOSFET to the N channel MOSFET. So both the gates are combined and it is combinedly, you can say this is G1 and G2, both are combined. Same way the drain of both the P channel and N channel MOSFET are combined. Okay, so we will be getting output from here and the input will be applied on the combined gate terminal. Okay, so this will be Vi, this drain combined, that will be your VO, and your source, okay, that will be combined with this terminal. Okay, over here we will be applying VSS and this will be grounded. Okay, this will be grounded. Okay, so this is the structure. So structure wise, what we have to do is, first of all we have to take N type substrate, then we have to form P channel MOSFET and N channel MOSFET, as we have seen the construction earlier. Same way we have to see it. Okay, after that this is added. Okay, on N channel MOSFET we have to add P material, on P channel MOSFET we have to add N material. Okay, now we have to combine this source of this and this terminal, that is we will be saying it is S2, where there we will be applying VSS. On this side we have to combine this S1 with this P material and we have to ground it. On this side we have to combine this drain D1 and D2. Same way we have to combine the gates. So whenever we are combining gate, we will be applying input over here. Whenever we have combined drain, we will be applying output. So this is a construction of the CMOS. CMOS logic family we have seen earlier. Okay, CMOS logic family we have seen its advantages. Okay, its input impedance is high, so faster switching speed, lower operating voltage. That means even you can operate at the lower voltages, 2.5 volt or less than that. So that are the advantages of CMOS. Already we have discussed. Now we are seeing construction wise CMOS. Okay, so we will see one basic, you can say, inverter with the use of the CMOS. Okay, so what we have to do is we have to take, you can say, P channel MOSFET and N channel MOSFET. This P channel MOSFET, N channel MOSFET. Okay, as we have seen, gates are combined and input is taken, drain is combined and output is taken from here. We have to apply the battery over here, that is we have VSS shown in the previous figure. So battery we will be applying over here. Okay, and this terminal which is grounded, which is shown over here in this figure like this. Okay, so this is the construction of CMOS inverter. That means nothing but NOT gate. Okay, so how your NOT gate will work, okay, in case of CMOS. So this is the input. So whenever we are applying input, we are applying between this point and this point. Okay, so what we are applying is on, this is N channel, this is P channel. Okay, so on between N channel we will be having VI that will be applied between that gate and source. So that is a VGS voltage. So based on the VGS voltage, as we understand in the MOSFET, there will be switching on and off. Okay, if it is less than threshold, then what will happen, that will be off. If it is greater than threshold, it will be on. Now it is N channel and P channel, so it is complementary. So whenever one will be on, other will be off, because one will be applying that threshold voltage positive and another will be getting negative voltage. Okay, so it will, one will be off and one will be on. Okay, so we will be seeing this one by one. Okay, so let's say first of all, whenever this V1 is equals to VDD is applied. Okay, so V1 is equals to VDD, that means between that terminal and this source terminal we will be applying some VDD, same voltage VDD. So the same, I mean whatever the battery voltage, same voltage we are applying over here. So what will be VGS for the PMOS? It will be 0 volt. And over here it will be some VDD value between gate and source for the N channel. जो नीचे का ट्रांजिस्टर है वो N channel है, ऊपर का है वो P type का है. So this will be on because we are applying some voltage which is higher than the threshold volt. Okay, so this will be on, but this is 0 volt between gate and source for the P channel, so this will be off. Okay, so this will be off, this will be on. So if we see the output voltage between this point and ground, it will be 0. So over here what we applied some positive voltage greater than the threshold, then we are getting the output 0. So NOT gate में हम क्या करते हैं, जब भी हम 1 देते हैं आउटपुट क्या आता है 0. So 1 यानी कि some positive voltage we have applied over here, we will be getting 0 volt in the output. Okay, now next case, whenever we will apply NOT gate 0 volt, we should be getting the output 1 volt. Okay, so over here whenever I'm applying 0 volt, that means this is grounded. So what will happen to this N channel MOSFET? This will be off. Okay, so that is open circuited, as you can see in this circuit, it is open switch. But what will happen to this? This will be applied, this 0. Okay, so this will be having some, you can say 0 volt. So this will be operating with the negative voltage, so that will be on over here. So this P channel will be on. So what will happen? This VDD will be coming over here, but there is open circuit, so all this VDD will be going over here. So your output will be VO is equals to VDD. So this is how you will be getting one output whenever you are applying 0 volt. Okay, so whenever VI is pulled to 0 volt, okay, NMOS will be off and PMOS will be on, so your output VDD will be high. So this is simple CMOS inverter gate. Okay, so this is about CMOS. I have to just give you construction and one introduction of the CMOS NOT gate. So this is about CMOS. Now there are some important parameters we need to understand in the FET. Okay, so there is one important parameter which is called the transconductor. So as we have understood that in the FET, okay, the output current ID, that will depend on the input voltage VGS. Okay, so both are related with the one constant term. Okay, that is called transconductance. So delta ID is equals to GM into delta VGS. Okay, so what this says is there will be dependency on the GM. Okay, so what we can say, GM is equals to delta ID by delta VGS. Okay, now how to find this? You can say transconductance. Now the name suggests it is transconductance. Conductance, as we know, it is I by V. Okay, resistance अपने खबर जो resistance is V by I. Okay, so conductance will be I by V. So this is I current, that is I, and there will be voltage VGS. Okay, so that is I by V. Now, okay, another term is trans. Trans means one quantity will be output, one quantity will be input. So in this case, we have ID, that is output quantity, and VGS, that is our input quantity. So that's why the name is transconductance. Okay, I think you have understood that point. Okay, now how to find it? So we have plotted last time, you can say, the transfer characteristic, where we have y-axis of ID and x-axis we have of VGS. Okay, so we were getting this kind of curve like this in the transfer characteristic. Now we have to find the slope of this. Okay, and if you take the slope, we have to take delta ID by delta VGS. So we will be getting transconductance from the graph. Okay, so we have to take the slope as shown in the figure, and then we have to project it on the x-axis and y-axis. So you'll be getting delta ID by delta VGS. So that is called the transconductance. Okay, so unit of that will be inverse of the resistance, that is called mho. Okay, so it will be mho, that will be the unit of this, or you can say Siemens, that is another way of saying the unit. Okay, that will be a unit of the GM. Another quantity which comes in FET, that is called dynamic drain resistance RD. Okay, so dynamic drain resistance is nothing but delta VDS by delta ID. Okay, now in the output characteristic, as we have plotted output characteristic, okay, if you remember the output characteristic, let me show you. Okay, so whenever we were drawing the output characteristic, it will be between VDS and ID. So for this curve, okay, either it is for FET or MOSFET, okay, we have to take the slope. Okay, so it is nothing but the delta VDS, okay, and delta ID ratio. Okay, so V by I, it is resistance, so delta VDS by delta ID. Okay, so it is delta VDS by delta ID. Okay, in the output characteristic will be having the different curves for the VGS value. So we have to keep the VGS constant. So we have to take any single curve, and then we have to take the slope. So this is the drain resistance. Okay, now another parameter which is called amplification factor mu. Okay, so amplification factor is itself says that what is the amplification you are getting. Okay, so it is delta VDS by delta VGS. Okay, so whenever we have to find it, we have to keep ID constant. Okay, and we have to find what is delta VDS and delta VGS in the output characteristic. Okay, so VDS, that is your output voltage, and VGS, that is your input voltage. So ratio of this two will give you what is the amplification factor. Now if you divide and multiply with the ID, okay, so you'll have another term which we have discussed recently, RD, and this term we have discussed, that is GM. So it is nothing but mu is equals to RD into GM. Okay, so that is amplification factor, quantity. Okay, now we will go for the biasing circuit. Okay, so see, in JFET, biasing circuits are not that much important of, as we have discussed in the transistor. Okay, so but I have to give it as a one point. Okay, or you can say overview. Okay, so let us discuss about the JFET biasing circuits. Okay, so first of all, we will see the JFET biasing circuit. In that we will see three circuits. Okay, in JFET we don't have thermal runaway, so we don't have to worry much about that. Okay, but whenever you want to use JFET as a switch, you have to operate with a fixed bias, and whenever you want to use JFET as an amplifier, you have to use either self bias or voltage divider bias. Okay, so we will discuss this circuits, okay, in overview. Okay, we will not go much in detail. Okay, so I will give you the circuit diagram and the equation. Okay, but if you don't, if you don't want to go in much detail, it's fine, because that is not much exam point of view, you can say, important. Okay, so let us discuss it one by one. But before going to that, okay, let me tell you that, there will be some assumptions we will be doing in the JFET analysis. always we will be taking Ig is equals to 0. तो गेट में से जाता हुआ करंट हमेशा FET में हम 0 ही लेंगे. Okay, because it is having very high input impedance, we will assume it is near to the 0, so it is 0. And one another thing is ID is equals to IS, यानी कि drain current is equals to source current. ये तो हमने पहले ही बोला था जब डिस्कशन किया था तब. ID is equals to IS. Okay, and this is the equation which we will follow. ID is equals to IDSS 1 minus VGS by VT for the JFET and D MOSFET. D MOSFET we will not see, but for JFET analysis we will be using this equation. Okay, now let us go for the first circuit. Okay, the first circuit is this fixed bias configuration. So in transistor also we were having the fixed bias configuration. So this is a fixed bias circuit. From here you will be applying your input voltage. From here you will be taking your output voltage. Okay, and this is simple JFET. There will be one resistor which is used with the drain, so it is named as RD. These are the coupling capacitors C1 and C2. What is the use of this coupling capacitor? This coupling capacitor is used to block whatever the DC contents coming from the input. Okay, C1 का function क्या होगा? You can say it is used to block the DC content from the input. Same way, whatever output is generated to block the DC from the output, we will be using C2. So in the output, we will be getting pure AC. Okay, so these are the two capacitors. Okay, now this resistor, that is resistor RG over here, which is used. Okay, and then there is a battery, which is negative terminal of the battery is connected with the gate. Okay, VDD will be used over here. Okay, now we are assuming Ig is equals to 0. So there is no current which is flowing through this loop. Okay, ये loop में से कोई current flow नहीं होता, तो ये resistor में से भी कोई current flow नहीं होगा. Okay, so that's why this resistor is not shown in the analysis part. Okay, so now in the analysis part, if we consider the input loop for the fixed bias configuration, then we will have one battery and one voltage drop VGS. Okay, else there is nothing over here. Source is directly connected to ground. Okay, so what we can say, VGS is equals to minus VGG. Okay, because there is no other drop available in my loop. Okay, so VGS is equals to minus VG because we have assumed that IG is 0. Okay, now coming to the output side loop, this loop. Okay, so VDD is equals to ID into RD plus VDS, and source is grounded. So VDS is equals to what I can say, VDD minus IDRD. Okay, see, if I am writing the equation in the output loop, VDD is equals to ID into RD plus VDS. Now if I am making the equation of VDS from that, what will be there? It is VDD minus IDRD. Okay, Vs, that is source voltage. Source voltage will be 0. Okay, I request Rusty to take the snapshot of all the participants. Okay, for the attendance purpose. So Vs is equals to 0 because source is directly connected to ground. Vd is equals to Vds because this is the only voltage drop we will have in the Vd. Vd is nothing but the voltage between drain and ground. So you will have only Vds. Okay. Vg is equals to Vgs. Okay, fine. So this is the voltage Vg. Okay, so what we can say, it is nothing but Vgs. ये drop है वही सीधा आएगा. Okay, so this is for fixed bias configuration, and fixed bias configuration, as I said, it is used in ohmic region. Okay, we will be operating in two region. Whenever we will be using as a switch, we will use fixed bias, and whenever we want to use it as an amplifier, we will be operating in the active region. Okay, so okay, if we plot the transfer characteristic for this circuit, okay, for one value of the RD, okay, we will be getting this kind of curve. So this will be your IDSS, this will be your pinch off voltage, so you'll be getting this curve. Okay, now according to this equation, VGS is equals to minus VGG. Okay, so according to the battery value, we have to mark one line over here because there is no relation of VGS with ID in this case. In the fixed bias, the VGS equation is directly VGS equals to minus VGG. So we will draw vertical line because VGS is on the x-axis. So we will have some constant value of the battery. Whatever the value of the battery, that line will be coming over that point. Okay, so let's say VGG is different, then we will have line over here. VGG is different, then we will be having line over here. Same way, let's say for one value of the VGG, we will be having line over it. Okay, now wherever it intersect with your transconductance curve, that is your transfer characteristic curve, okay, that will give you the operating point for the fixed bias. Okay, that will be giving you the Q point for the fixed bias. Okay, now, okay, how this fixed bias will be used as a, you can say, switch. Okay, so we have to operate in the ohmic region. So okay, you will be drawing one line which is giving you the relation between your ID and VDS. Okay, because we have seen that VDD is equals to IDRD plus VDS. Okay, so there will be one line. Okay, and you will have the so output characteristic curve. So you will be having intersection over here. That will be your Q point. So what you can see over here is we are operating in the ohmic region. So it will be, FET will be offering some resistance according to this line, because this line is showing you VDS and ID. Okay, so the resistance RD will be VDS by RD. RD is equals to, we have seen that it is delta VDS by ID. Okay, so VDS by ID, we will be having some resistance, so it will be shown as a variable resistance over here. So FET just will be replaced by one resistor RDS depending on this Q point. Okay, depending on this line, okay, your resistance will be varying. Okay, so we are operating in the ohmic region. So if we keep the value of you can say this resistance less, it will be behaving as a on switch. If we are having higher value, then it will be behaving as a off switch. So okay, we will be having VDD is equals to ID into RD plus VDS. Okay, if we say that on switch, then VDS is equals to 0. If we are behaving the FET in the on switch, then VDS is equals to 0. So at that time, according to this equation, it will be only ID saturation that will be like it is in saturation mode. ID uh, highest value of the current, so ID saturation into RD. So from this equation, we can say ID saturation is equals to VDD by RD. So whenever you want to operate the FET in the saturation region, this ID saturation value, you just keep less than IDSS. So then only your curve or your line will start from here. Otherwise, it will touch over here. Okay. So this is ID saturation less than IDSS. So that is one condition whenever you want to operate in the ohmic region. So ID saturation formula in the ohmic region will be this VDD by RD. Okay, so this is how in the fixed bias we will be operating, and how fixed bias will be offering resistance. Okay, that is we have seen right now. Okay, so this is fixed bias. Another configuration for the active region is self bias configuration. Okay, so self bias configuration, we will be having only one battery over here. There is no VGG battery in this, you can see. Okay, so uh, what we will do is, okay, we will be having VDD, okay, and then we'll be having resistor RD. There will be source resistance RS. There will be one resistance RG over here, okay, and there will be input voltage over here, and there will be output voltage. We will be taking it from here. Same way C1 and C2 are connected, okay, and we will be doing the DC analysis for this also. Okay, so for the DC analysis, uh, 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 we will be doing DC analysis for this. Okay, so if we write the output side loop equation in this, then we will be having VDD is equals to IDRD plus VDS. Okay, I think this circuit is wrong. Okay, I have by mistake I have kept it of the previous one. Okay, but let me show you from some other source. Let us discuss it from here. Okay, so VDD is equals to ID into RD plus VDS plus ID is equals to IDSS. We have taken the assumption earlier that ID is equals to IS. The starting may we have taken assumption, no? IG is equals to 0 and ID is equals to IS. So what we will write as VDD is equals to, okay, ID into RD, okay, plus VDS plus, you can say, ID into RS. Okay, because both the currents ID is equals to RS. Okay, so we can take the common from this two terms, RD and RS will be in the bracket, ID will be common, and this will be VDS. Okay, so this equation is like this: VDS is equals to VDD minus ID into R. Now from in the input side we will have id into rs. Okay, so there will be this v vgs, or you can say vgs is equals to id into rs. There will be no gate current, so there will be no current flowing through this, so this will be just short circuited. So we will be having in the input side loop, okay, input side loop, we will be having vgs and id into rs. So vs, or you can say vgs, okay, that will be equals to id into rs. Gate current is 0, so there is no drop, so gate is directly shown short circuited, so vg is equals to 0, vg is equals to 0. Now you utilizing this above formula, we can say what is vd. Vd is nothing but vds plus vs. Okay, so what is vs? Vs is nothing but id into rs, and this voltage drop is vds. Okay, so it is vd is equals to vds plus vs. Okay, so if we make the equation of that vds, okay, so vds is nothing but vdd minus idrd. Vdd is equals to, okay, you can say vdd is equals to id into rd plus vd. Okay, so from this, if I make the equation of vd, it will be vdd minus rdrd, vdd minus idrd. Okay, and keeping that value into this, okay, we will be having vdd minus vrd, that is this this drop. Okay, so this is not much important because I want to just show you this is this curve. Okay, so this is for this circuit. If you plot transconductance curve, you'll be having this curve. Now, how to find Q point in this? Okay, there is one equation which is VGS is equals to minus ID into RS. In this circuit, this equation is important. We see this is we have grounded. So you have only two drops in the input side, VGS and this IDS, but both are having different polarity. So we will write VGS is equals to minus ID into RS. So now what is the relation of VGS and ID? That is important. So we have to plot this relation. So it will depend on the resistor RS. Okay, so we'll be plotting that. Okay, and we will be having this line, okay, which represent VGS is equal to minus ID into RS. So based on the value of the RS, you will be having either this line or you will be having this line, okay, starting from origin. Okay, so that depends on the value of the RS. So now whatever the value of the RS, you just plot it, and wherever it intersects, you will having the operating point. Okay, you will be having operating point, and that will be in the, you can say, active region. Okay, not in the ohmic region. So that will be used for the, you can say, your amplification purpose. Okay, another one which is very popular in transistor also, we have seen that voltage divider transistor configuration is widely used. Okay, so voltage divider जैसे transistor में था वैसे ही इधर ही है. Okay, same way. Why it is called voltage divider? Voltage is divided through this resistor R1 and R2. There will be resistance with the drain. There will be resistance with the RS. Okay, there will be bypass capacitor CS, which is used to, you can say, there will be negative feedback source by the source resistance. To reduce that effect, we use this CES resistance. So all the AC signal will be passing through this. Okay, and if the meeting ends, we will be joining again. Okay, there are 9.5 minutes remaining. Okay, so this capacitor will bypass the AC signal. For DC, it will be flowing through RS. Okay, so it will be stabilizing your Q point. Okay, this is, you can say, C1 and C2 I already explained. Input will be applied from here. Okay, output will be taken from this point and ground. Okay, and okay, this is the circuit. Fine. So not going into much analysis, okay, but this is the voltage divider. So what is the rule of the voltage divider? Already we have seen. This is the gate terminal, so the voltage at this point is called VG. So VG is equals to R2 divided by R1 plus R2 into VDD. Okay, because it is voltage divider. Okay, so we will be utilizing the voltage divider rule over here, but there is a gate current 0 over here. Okay, so writing on the input side, okay, there will be some voltage VG over here. So VG minus VGS minus VRS is equals to 0 in the input loop. Okay, if you write the loop equation over here, then we can say VG is equals to VGS plus VRS. So taking that on the left hand side, we will say VG minus VGS minus VRS is equals to 0. So from this, if we make the equation of VGS, this is important. Why? Because we want to draw that line in that transconductance curve from this. So it says that VG minus ID into RS. VG minus ID into RS. Okay, from this equation. Okay, ID into RS, that means your VRS. Okay, now from this we will be, I'm not going into this, you can definitely see from the output side and you can understand this equation. My important thing which I want to explain you this, for this curve there will be transconductance curve like this. Okay, now what we have to do is we have to plot the line curve based on the relation of VGS and ID. So if I plot this, there will be VG, that will be some constant voltage, minus ID into RS. So it will not be starting from origin, it will be starting from some voltage positive VG, and it will be intersecting on the y-axis at some point where VGS is equals to 0. You will be having ID is equals to VG by RS according to this equation. Okay, in this equation, if we keep VGS equals to 0, what you will be getting? You will be getting ID is equals to VG by RS. So you mark that point, connect this 2 point, extend that line, it will be intersecting at one point, that will be your Q point. Okay, so operating point for the voltage divider, how you can find graphically by this method. Okay, again this will be used for amplification purpose. Okay, so these are the three circuits which we have to see for the FET bias. Okay, so this is voltage divider. So my lecture, almost we have covered all this content. Now if you have any question, you can ask. Okay, you can ask the questions.